What's up, everybody? How's everybody doing? Welcome to question 8 of 25 in our Power 25 series. This is the 25 most essential questions that you need to kind of ace these technical interviews and to kind of give you your bang for your buck on LeetCode. So without further ado, let's go ahead and get started. This problem here is a great problem. It's called coin change. I think many of you have heard of this problem. This is actually a really cool problem too, and it's kind of teaching one of the most foundational things called dynamic programming, which I hope that we can both learn today. So we're given coins of different denominations and a total amount of money amount. Write a function to compute the fewest number of coins that you need to make up that amount. If that amount of money cannot be made up by any combination of coins, return -1. And you have infinite number of each type of denomination. So we're given denomination, so think of this as like a penny. There's a thing called a 2 penny and then a 5 penny, and we want to make an amount of 11 coins, so the amount of 11 pennies. So the output is 3. Why? Because you can make 2 5 pennies and 1 penny. 5 plus 5 is 1. That is going to equal to 11, and the number of coins to make that was 3. This one, we have an amount of 3, and the number on our denominations is 2. So theoretically, we only have denominations of 2, and we have an amount of 3, so we return -1 because we don't want to do anything. So how are we going to attempt this problem? And for this problem, I want to gather some intuitions. What sort of a lot of people do at the first time. And a lot of people think, oh, this might be a greedy algorithm problem, where we kind of start at the very end, and we kind of iterate down from the most denomination to the least denomination, sort of subtracting. So what do I mean by that? I mean, let's say that we're given this problem here. Or let's actually go to the this one here. So we have 1, 2, and 5. So we can sort of 11, we can say, okay, is 11 greater than 5? Yes. So we're going to add 1 to our count, and we're going to subtract 5. We're going to have 6. Is 6 greater than 5? Yes. We're going to subtract 1. Now we're at 1. Is 1 greater than 5? No. Is 1 greater than 2? No. Is 1 greater or equal to 1? Yes. So we're basically going greedily from the highest denomination, and we're subtracting using a while loop or something like that, which is great. It works for that problem here. But let's see the intuitions and how this fails. Well, if n is equal to 380, well, we're going to keep scraping from this 100, and we're going to have 3 coins, right? Because that'll be 100 plus 100 plus 100, and our new n is going to be 80. Is 80 greater or equal to 100? No. Now we're going to move on to 90. Well, is 80 or greater or equal to 90? No, it's not. So we're going to move to this 1, and this is going to loop 80 times, right? And we're going to get, it's basically saying we have a 100 coin plus another 100 coin plus another 100 coin plus 1 plus 1 plus 1 plus 1 plus 1 all the way to 80, which would give us a 380, but this would take 3 plus 80, which is equal to 83 coins. And kind of looking at this intuitively, if we have denominations of 1, 90, and 100, we can do better than just making 83 coins, right? Well, we can actually do way better. We can actually do 100, or we can do 2 100s, and then we can just do 2 90s. And the actual answer we want to get is 4, but our greedy algorithm is giving us 83. So this is where our greedy intuition fails. So how are we going to combat this problem? So this is the concept of, let's suppose, before we even talk about dynamic programming, let's think about it at a very intuitive sense. If we want to know the number of coins that we need with the amount of $7, what if we make an array that builds up to that amount of $7 from 0 all the way to that amount n? So what that means is, okay, we want to know the amount at the very end of the array. Well, let's start at the beginning. What's the amount that we can make with 0 coins? Well, what's the minimum number of coins we can make with amount of 0? Well, the minimum number of coins we can make amount of 0 is just 0, right? Because if we don't have an amount to begin with, we can make 0 coins. This is our base case. Now, we kind of iterate through we build this entire array, and we can say, okay, if we keep building and we know the amount of coins needed what's the minimum number of coins we can make by 1 coin? What about 2 coins, 3 coins? And we build all the way up to our final answer. So what I just explained to you in a nutshell is basically the foundations of dynamic programming. We're actually, you'll see what we're going to do. We're going to dynamically sort of get this new output based on our past solutions. And that sounds very confusing, but let's go ahead and get started. So what do we need to realize here? We need to realize this formula, and we'll get to this later. So what we're going to do is we're going to loop through the denominations of increasing order, and we're going to say, okay, well, we're going to slide our little, we kind of only look at everything to the left of this. So let's look at everything to the left of this. We have a 0 and a 1. So intuitively, if we're given a denomination of 1, 2, and 5, what is the minimum number of coins that we're going to make? for our 1 denomination, or if we only have an amount of n equals 1, right? So if this is just 1 right now, well, it would just be 1, right? Because we can just make the 1 coin. And okay, that makes intuitive sense, but if we kind of do a formula, it would be the minimum of our original dp of I, and it would be 1 plus the dp of I minus our denom. I'll say d for denom. So what this looks kind of confusing. What do I mean by that? Well, notice how at the very beginning, all of these arrays are initialized at infinity, which is basically saying anything of any value that's not infinity will get overwritten. So at the very first iteration, the minimum of dp of 1, right, is just going to equal to our current dp of 1, which is infinity, because we initialized it to infinity, and 1 plus the dp of I minus d. So I right now is 1, and d right now is 1, because our pointer is on the denomination of d. And what is that basically saying? 1 plus the dp of I minus d is 1 plus the dp of 1 minus 1, which is the dp of 0. So what this is basically saying is, we're going to choose, every time we do 1 plus, think of it as we're taking a coin out of this denomination. So I'm going to take a coin out of the denomination of 1, okay, and I'm going to add it to the number of ways that I can, the minimum number of coins I can make at index 0. So it's going to be 1 plus 0, and that would give us 1 plus 0 is 1, and we're going to get the minimum of infinity and 1, and this gets overwritten to 1. So if we just think of it and our n equals 1, the minimum number of coins we can make with the amount of 1 is just 1, because it would be just this 1 coin. And that sounds like a lot of work, but it makes a lot of sense intuitively. So let's slide our window, and let's go to the 2. All right, so now we're going to do the same exact thing. So the dp of 2 is just going to equal the dp of 2, which is just infinity, and 1 plus the dp. Remember, we're going through we're going through all of these denominations in increasing order. So our pointer is going to the 1 and the 2 and the 5. And the reason that I didn't care about traversing to the 2 and the 5 when we were at this index 1 is because 2 and 5 are greater than 1, so we don't need to traverse them yet, right? Because we're trying to find the number of coins given an amount of 1. There's really no point in looking at denominations that are larger than that. So let's go to the denomination of 2. 1 plus the dp, remember our pointer is at the denomination of 1. 1 plus the dp of what? 1 plus the dp of our I, which is 2, minus 1. So we're saying, okay, we're going to grab from this 1 coin. So we're doing 1 plus, right? Because our denomination's at 1. The dp of I minus 1 is just the number of coins we made right here. So this would just be 1. So it would be 1 plus 1. So what does that equal? So we're basically saying, okay, we have an amount of 2. We can choose 2 1 coins. 2 1 coins to make 2. That's great. So let's go to the next pointer. Okay, we're at the 2. So the dp of 2 is going to equal to infinity and 1 plus the dp of 2 minus 2 now. Okay, what is that saying? It's saying we're grabbing from the denomination of 2, right? And it's going to be 1 plus, right? Because we're grabbing from the denomination of 2, and we're going here. We're saying, okay, we can use a 2 coin plus the minimum number of coins to make at the denomination of 0. Notice how we're doing a distance. The distance from our amount minus the denomination. And we're pulling from the minimum number of coins we can make at that distance output. Okay, so that is just 0. So 1 plus the dp of 2 minus 2 is dp of 0, which is just 0. This overwrites to 1. So we get the, remember, at the first time when we do the dp of 2 minus 1, this turns into 2, right? And then we overwrite this value because, yeah, we can have 1 plus 1 equals 2, but what's something better? We can just do a 2 coin, and that equals 2. So that overwrites to 1, which is intuitively fine. Okay, so let's slide our window. Okay, let's go a little faster now. The dp of 3. Okay, so the dp of 3 is equal to, right? So dp of 3 is equal to infinity, or the minimum of infinity, and 1. Remember, our pointer is at this 1, and I'm not traversing the 5 because there's no need, right? Because the 5, the denom is already bigger than the amount. So 1 plus the dp of 3 minus 1, which is the dp of 2, right? Because we're on this I minus d, 3 minus 1. Okay, so we're grabbing from the 1 coin, and we're taking from the minimum number at the 2 coin. So that's basically saying, okay, I can do a 1 plus 2, that equals 3. right? If I'm grabbing from the 1 coin and I'm taking from the minimum number I can make at this index of 2, because we established before that the minimum number of coins at this one is just 1, and that's just literally just the 2 coin. So 1 plus 2 is equal to 3, and the minimum number of coins here would be 2. And let's think about with the denomination of 2 now. So the denomination of 2, we're grabbing the 2 coins, so 2 plus, and then we do the distance between 3 minus 2, which is basically going to go here, right? Because we're going a distance of 2 now. So it's saying, okay, I can do the 2 coin first, and then I can do the 1 coin, the minimum number of coins to make 1 coin. And I can either have 2 plus 1 or 1 plus 2, whatever you want. It's still going to be 2 coins. 5 doesn't matter. We're going to keep moving on. Okay, let's go to 4. So what's the dp of infinity and 1 plus the dp of 4 minus 1, right? Because our pointer is going to be on this 1 again. Well, that's just going to be the dp of 3. And the dp of 3 we establish is 2, right? So this is just going to be 2. And 1 plus 2 is going to equal 3. So the minimum of infinity and 3 is just going to be 3. So what is that basically saying intuitively? Okay, let's grab from the 1 coin and let's find the minimum of this one. So it can just be 1 plus 1 plus 2. Or we can, whatever these two are. Okay, that's great. So this is going to be 3. But okay, let's do this again. Remember, we're going to the denomination of 2 now because this is at 4. So we're doing, well, now our minimum is 3. And 1 plus the dp of 4 minus 2. Well, what's the dp of 4 minus 2? Well, we're going to go a distance of 2. And we're doing 1 plus the dp of 4 minus 2. That points to the 1. So it's going to be the minimum of 3 and 2. So what does that mean? I grab from the 2, which is just going to be a 2. And plus the dp of the minimum number of coins I can make with amount of 2, which is just 1, which we established is just another 2. So I can either go to 4 doing 1 plus 2 plus 1 or 2 plus 2. I want to go 2 plus 2. So I'm going to take the minimum and I'm going to go to 2. Okay, moving on. Okay, let's go to the 5. Now, this is where it gets cool because we have 1, 2, and 5. Okay, let's just do this a little bit faster now. So the dp of 5 is equal to infinity, and the minimum of 1 plus the dp of 5 minus 1, which is just 4. So the dp of that we established at 4 is just 2. So it would be 1 plus 2, which would be 3. Remember, okay, our denomination is going to move on to the 2. Okay, let's do this again. So it's going to be 1 plus the dp of 5 minus 2, which is the dp of 3. So basically, we're going to the dp of 3 now, and that's going to equal 2. So 3 and 3 is just going to be 3. The minimum of 3 and 3 will just be the same number 3. Now, this is where it gets interesting. So we have a 3 here, and we're doing 1 plus the dp of 5, right? Because our I is 5, and our denom is 5. So we can either go 2 plus 2 plus 1, right? Because that was what we established is the min coins of 3. Or we can just take the 5 coin, right? Because this distance is going to go all the way to this 0. And we're going to take the 5 coin, right? Because it's going to be 1 plus the dp of 5 minus 5, which is just the dp of 0, which is just 0. So it's going to be the minimum of 3 and 1, and this is going to be a 1. All right, we're almost done. So let's go. Slide our window to the 6. Nice. So let's go to the 6. So we're going to do the same exact thing. So our thing is going to be at this 1. Okay, so can we go, so it's going to be infinity, and the dp of 6 minus, the dp of 6 minus 1, which is the dp of 5. So the dp of 5 was established to be at 1. And look how this is like dynamic programming, right? We're dynamically changing and kind of building off of our kind of last output, and we're using that. So, okay. So the dp, 1 plus the dp of 6 minus 1 is just going to be 2. Because that's basically saying, okay, we can take the 5 coin and then we can take the 1 coin. And then the 2 coin, okay, well, let's do the same thing. So let's say we're at the dp of 6 now. So we have 2. And our precedent is 2. All right, so then let's do 1 plus the dp of 6 minus 2, which would give us 4. So 1 plus, what's the dp of 6 minus 2? That's 4, and that's established at 2. So 1 plus 2 is 3. 2 wins still. Now let's go to the 5, and this is going to also give us 2, because we can either do 5 plus 1 or 1 plus 5, whatever you want. So this is going to establish the 2. Awesome. So now let's go to the 7, and we're almost done. Okay, let's go to the 7 and see how this works. So it's going to be the minimum of infinity and 1 plus the dp of 7 minus 1. So this is established to 2. So 1 plus the dp of 2, this will be 3. Okay, so now let's do it with the denomination of 2, right? The denomination of 2 here. So 1 plus the dp of 7 minus 2, which is the dp of 5. Oh, okay. So we have 1 plus 1, which is just going to equal to 2. Why? Because that's basically saying, okay, let's choose the 2, right? Because we're on the denomination 2, and then let's add this 5 coin, which gives us 7. And we're going to do the same thing with 5, and it's just going to be 5 plus 2. Because, right, let's choose the 5, and then let's add the 2 coin. No matter what you do it, you'll get 2. At the very end of the day, you're going to get 2 minimum coins. You return the last indice of the DP array. And that's it for the high-level overview. Time complexity would actually be, you can put any kind of bound on it. I like to do O of n times d, where n is the, so basically we're going through every single up to our n. And for every time we're going through our denominations array, right? So we're going through our denominations array, where d is the length of our denominations array. And space complexity would just be O of n, because we're creating an array of n elements, and each element sort of has all the indices up to our amount. So that would be time, and then this would be space complexity. So hopefully that was good, guys. And if that still doesn't make a little bit sense, hopefully the coding implementation will be a little bit better. And let's go ahead and jump into the code. Alright, guys, so let's go ahead and jump into the coding implementation. This is actually way more straightforward than kind of the walkthrough. I know the walkthrough is a little bit hard, but hopefully this will kind of solidify the ideas that we have in our mind. So we're going to make that DP array that we said. So we're kind of establishing it to infinity, and this is a list comprehension in Python. And, oh, sorry, this should just be the range of the amount plus 1. So this basically makes our DP array that we have here. And that just establishes it to infinity. All right, that's great. Let's do our base case. So our base case is the dp of 0 is equal to 0. Okay, so then let's do the for I in range. Okay, so let's iterate through our dp array, which is kind of iterating through all the amounts. And then for every denomination, right, in our coins, well, if the denom is less than or equal to I, right, we only want to run the code when it's less than or equal to. Because if our amount is lower than our denom, we don't want to traverse our denom, right, because that would just be kind of silly. So, right, this is the golden sort of one-liner that we have. So the dp of I is equal to the minimum of our current dp of I, and 1 plus the dp of I minus our denomination amount. That's awesome. And we're actually done. So we can just return the dp of -1, which is the last dp index array, if the dp of, the dp of -1 array is not equal to the float of infinity, right? Because if it's not equal to the float of infinity, then we know that we have an actual DP. If it is, then that means that nothing has changed, right? And this runs perfectly fine, O of n times z time, and O of n space. So thank you guys so much for watching. I really appreciate sort of if you stuck it through to the whole video. Thank you so much. You guys are really awesome. I'm going to try to be more consistent with it, and hopefully this kind of helped you solidify dynamic programming and what it is. Thank you so much. Make sure to like and subscribe, and I'll see you in the next one.